So after all my cussing and horrible words here. All right, so we were talking about we're doing the comparison between the different types of common big O notation. So n times log n is only slightly slower than linear big O of n. And then so we got down here where we were talking about our logarithmic time. So as your input doubles, the lifetime increases, but it's only by a constant amount, which is awesome, because it doesn't get really big really fast. And then we're talking about any algorithm that has the data remaining, so like your binary search, like Evan said. So that is the remaining to be processed on each iteration. That ends up being this big O log of n algorithm that having that binary searching. So let's look at some actual practical problems because all this theory really kind of like, I don't understand the point. Okay, so practical problems when we're using big O. So you have this algorithm and it runs in linear time, or O sub n is linear time. And you are given the following. So our input size is 10, and then the algorithm of an input size of 10, it takes 2 milliseconds to run. Okay? So with that information, and you're giving an input size of 500, then we could make the calculation and come up with that 500 would actually run in 100 milliseconds, right? Because we can just do the math. So as our input size jumped, or was a multiple of 50, so from 10 to 500. All right, so you see that a multiple of 50 resulted in a multiple of 50 because O sub n is linear. There's not any crazy math associated with it. It's just based on math. So if we can do an input size of 10 to 2 milliseconds, then an input size of 500, multiply times 50, that gives you that 100 milliseconds. So that totally makes sense from a math perspective, right? So this is linear, which is awesome because that's pretty easy for us to understand. But when we're dealing with big O, it's not really exact. It's really just that upper limit. Remember we were talking about Wednesday that it's just an evaluation because we drop everything except for the most significant impact. And so like if n squared is the most significant impact, it didn't matter that our function was 4 times n squared plus 3n plus 10. What matters is the most significant impact is that n squared. And so that's why it's not an exact. It's just the upper bounds on the running time. And so when we're saying that, when we come up with that big O, it's just saying that of our function, the amount of time it runs is that algorithm runs in big O of that function there in the parentheses. That's how long it takes. But the exact, that's our upper bound. But the exact running time is actually that constant. So we get that constant value, and it'll get us closer to the exact running time of that constant. So what this does for us is that gives us that opportunity to solve for C. And so when we solve for C, then we can use that value to actually compute our running times. And so here, we have an algorithm that runs in n squared time. So the input size is 4, the running time is 10 milliseconds. So how long will it take to run at an input size of 16? Okay, so up here, we could quickly look at this and go, oh, well, we started with an input size of 10, now we have 500. The impact was a multiple of 50, so we just multiply our milliseconds by 50, so we end up with 10. And so it totally works. Well, now when you're dealing with n squared, well, it's not that super simple. I mean, some people are really super great at math and they could just do, calculate this in their head. But people like me, who has become horribly dependent on computers to do the math for me, I would actually have to do the equation. So here you see that our input here is, we have our big O's n squared. And then here the input size is 4. And so we're going to change our n to be 4. So our big O of 4 squared and our running time is 10 milliseconds. And so if we have an input size of 16, how do we determine how long it runs? So first of all, if you remember, we go all the way back up when we came up with our two equations. Like, why the heck would we have two equations? Well, so you can come up with these calculations. So here, where we do this second equation, where is that? Okay, so remember here, we said f of n is our equation 4 times n squared plus 3n plus 10, and we just say that, so our big O is the n squared, so we create that second function, the g of n is equal to n squared, okay? So that's where we're at, and it doesn't matter what that letter is. Remember, previous slide, we said we don't care what that letter is. It could be any letter. It doesn't have to be G. Where is that damn thing? I know it's in here. Wait, be patient. Patience is not my strength. I can assure you that. Except with you guys. I have all the patience in the world with you guys. After that, forget it. All right, fine, whatever. Okay, so somewhere in these slides is that it doesn't matter what that letter is. It doesn't have to be G. It doesn't have to be R. It doesn't have to be Q. It doesn't matter what it is. What is it going to be? So we get back down here to slide 40. Okay, so in this case, we're going to use the letter T. Doesn't matter, right? Okay, so here we're going to set that equal to our constant times the n squared. So the T is referring to our running time. So we use T because, you know, it's time. And so the whole alliteration thing kind of makes sense. So now we have an input size of n. So now we can put in the data so we can solve for our C. So up here we said we have n squared, right? So here's our n squared. And we're looking for that constant value. So we put that C in there times our n squared. And then we said maybe it takes 10 milliseconds. And so we come up here and we split T with a 4 is equal to our constant squared. Our constant times 4 squared is equal to 10 milliseconds. And so if we do the math, you know, all that good algebra stuff that we learned a long time ago, our C ends up taking 10 divided by 16 milliseconds. And so now, how do we plug that back in so that we can find out T of 16? They told us what T of 4 is. But how do we do T? So now we know what our constant is. We solve for that C right here. So now we can answer that question. So we plug in our T of 16. So our constant times 16 squared is really 10 divided by 16 times 16 squared. And that ends up equaling 160 milliseconds. Because math is fun. Okay, so another problem here. So you have an algorithm and it takes log 2n time. And so we have an input size of 16 and its running time is 28 milliseconds. So what if we had an input size of 64? So first we have to solve for our constant, right? And so here our big O is log 2n. So here's our log 2n with our big O. And then we have our C times that so we can figure out our constant. And then so our T sub n. So here we put in the actual data that we're given. We're given the 16. We have our constant C times log 2 of 16, and that equals 10 milliseconds. If we do the math on that, we end up with C times 4 is 28 milliseconds, and so therefore our C is actually a 7. And so now we can turn that around, and we can plug that value in as we're trying to solve where T is actually 64. And so here's our calculation. T of 64 is equal to our constant times log 2 and 64, which our constant is actually the value of 7. So 7 times our log 2 of 64 is 7 times 6, and so we end up with an answer of 42 milliseconds. I love these slides. They just crack me up every time. So what I want to see really quick is, yes. Why do you gotta ask me that question? Log 2n is, so choose to what power gives you 16. Okay, right? So 2 to what power gives you 64? See that? So 2 to the 6th power is going to give you the value of 64. It's how many times is 2 raised to that power to get you that value? I pretend I don't know math, but you know. It's just self-preservation. Because otherwise you start asking questions about discrete. I don't want to. No, actually, it would be kind of fun. Do you guys actually enjoy that class? No?
I myself.
He does. Oh my God, look at the. Who likes discrete? That's cool. Are you guys math junkies? I know you're a math junkie. You guys math junkies?
I'm a math major.
You like discrete? You're not taking it yet.
I took logic at 3. It's very similar to discrete, but it's more advanced.
All right, so we have 6 minutes. You think this will run in 6 minutes? You're trying this. 7. I'm plugged in now. Totally good.
That would make it even funnier.
Oh, I know, right? Watch the battery crash and burn. Like, oh, I can't handle it. Oh my God. The lights are dimming. I just want to see how long it takes to run 20. Because somebody said that after 13 it wasn't practical, but on my computer it's like, yeah, I'm cool.
Put the number it actually goes to 1,028,000.
Okay. So this is a really good algorithm analysis to do.
Open task.
What's that?
Open task.
Oh yeah, yeah.
The sun actually ever make it up here?
I don't know.